One more talk before lunch. It's another garbage collector talk. You already know these guys. It's like their 15th talk so far this conference. So let's just get on with it.
We're going to talk about garbage collection again, so I hope that it's of interest to you. This time we're going to go over small allocation, garbage collection, various DRuntime integration issue, this kind of stuff. Also ID for future work that we want to do. Yesterday we focused on large allocation, but actually when we look at the profile, large allocation is like a blip in the performance that we use for it. Most of the heavy duty work is going to be either the back phase of the garbage collection or small allocations. So that's where, like performance constraints are more important. For large allocation, the concern is more, do we accumulate fragmentation over time? So we go over small allocation first. In a way similar to allocation class that we use for pages in blocks, we have size classes for small allocation. They were kind of the same, not exactly the same. That would not be fun otherwise, but mostly the same. So we have a set of sizes, and as they get bigger, the step between them gets bigger as well. Many other people have worked on that before us, right? We are inventing nothing here, but we find that doing it that way is a nice balance between what we call internal fragmentation. So it's like, okay, here is the size of the thing I'm trying to allocate, and here is like the size class is bigger than that, so there's some wasted space here. That's internal fragmentation. And external fragmentation is, well, if I had like one size class per size for every single possible size, many of them would get like one or two allocation in the program, but we would allocate like a full page to do many of those, and we would waste a lot of space that we don't have demand in the program to fill, and that would be external fragmentation. We have the concept of extend class, which is kind of the same, except it's like the size class plus 1 and 0 it indicates that it's a large allocation. Those size classes have all kind of property. We have like a documentation that explain them and what we should expect out of each of them, but we don't want to cover that here. That would be too much material. So now small allocation, we group them into slabs. How do we allocate a slab? Kind of like a large allocation. A slab is going to be 1 pages, 2 pages, 3 pages. It depends on the size class, but like a small number of pages. And we're going to cut the slab into smaller chunks in there. And we are doing small allocation from those small chunks in the slab. The slab is also represented by an extent, just like for large allocation, except some data in the extent are interpreted a bit differently to indicate which slot are used, which slot contain metadata and finalizer, this kind of stuff. Because there is a limited number of bits in there on smaller size class that have more elements in there. Some of the feature we do not support. For example, the smallest size class is going to be 8 bytes, which is like the size of a pointer effectively. But in that one, we can have 512 elements in the page, and the slab is 1 page. And so we don't have enough bits to support finalizers, for instance. But at the same time, the finalizer would use 1 pointer size, to be described in the slot. So it would be good only to allocate the 0 size things with a descriptor, which is like a bit suspicious as a use case. But generally, like, all the features are not going to be supported for the smaller size classes. And when you need them, then the GC is going to just bump you to the next one that support the feature. We separate the slabs into 2 categories, the one we call dense and the one we call sparse. The criterion is very easy. It's like, are there more than 16 elements in the slab? Why is that? Because if we have less than 16 elements, we have good chances that they all go away at once and that we can free the slab. If we have more than 16 elements, there are good chances that the slab is going to be very long-lived or even immortal, because the probability that all the elements that compose the slab are freed all at the same time without new ones being allocated in there is becomes very low. And so we put the dense slabs in their own blocks, right? The blocks that contain dense slab are going to contain only dense slabs, and the sparse one we put them in the same blocks as we put large allocations, because those are allocations that are likely to go away and the block is then likely to be freed. All of that is obviously like heuristics that's probably going to have to be tuned as we try with more applications, but it works well enough for us. All right. Now I want to introduce the concept of arena and bins. We lied to you slightly yesterday when we presented the patch filler. We said there is like 4,096 on them. But actually, like, there is 4,096 arena, and each of them contains a page filler. And in addition, the arena contains a set of bins for each size class for small allocations. Kind of like the page filler has bins for block, the arena has bins for slabs that are not full. So that subsequent allocation of a given size class, we can go in the right bin, see the heap, and extract slab from them and allocate from there fairly easily. So the arena is going to be chosen based on the CPU you can run on, and yeah, pretty much the locking granularity is going to be on the bin. So if we have like even many threads that touch the same arena, if they don't touch the same size class, then they don't run into each other. So that's roughly what it looks like. And like, look at those colors. Isn't it beautiful? So we have the page filler in small that we saw yesterday. So if you cannot quite read that, it's okay. Go watch the talk from yesterday and you're going to have the same picture. But otherwise, in addition, we have this set of bins for each size class that contain a heap of all the slabs that are ready to be allocated from. So the slabs that are not full and also not empty because they would be freed. All right. So we go back to the page descriptor. We saw the same slide yesterday, but now we have a couple of things in there that makes more sense. So first, the 6-bit extend class here. So as we've seen, if it's 0, it's a large allocation. And if it's like 1 or more, it indicates which size class for slabs you are looking at. And arena index, we told you that, well, it allows us to retrieve the page filler. Really, it allows us to retrieve the arena, as the name indicates, and the page filler is going to be in the arena. The 4-bit index is where this page is, like in a slab or in the large allocation. Because it's just 4 bits, we cannot really do anything with that for large allocation because they can be more than 16 pages. But we have no slabs that are bigger than this. So when we are talking small allocation, we can rely on the index to find the beginning of the slab. And that gives us a very nice way to compute the index of like any element in the slab from a pointer with just the information that we have in there, which is quite important because we don't want to be chasing a bunch of pointers, for instance, when we free. So to do that, we are pre-computing a multiplier and a power of 2. You know, it's the good old trick to avoid division. Division, by the way, for people that don't know, division are very, very expensive on modern machines. We are talking like sometime up to 80 cycle for a 64-bit division. It's really, really expensive. Like short of a memory miss, you know, a memory cache miss is probably one of the most expensive thing you can do. It's more expensive than the branch miss prediction, for instance. So what we're gonna do, like if we start from a pointer, whittling it down to find the page the pointer is on, then we use the index of the page descriptor to find the beginning of the slab. And then between the difference between the pointer and the slab, we find the offset we are in within the slab. And then with those pre-computed constants, we multiply, we shift, and boom, we have the index that is in there without any kind of division and without fetching like a bunch of data around. We can do all of that from the page descriptor, which is quite important because in terms of allocation, this is where we spend like 90+% of the time in the GC on doing this kind of stuff. Then we have a thread cache for every single thread. What we do, like, you know, the arena and the stuff like that, they are shared data structure. Even if they are pair core, there can be some contention in there. And also, they are concerned that you cannot stop the word when you are in the middle of an arena operation because you can hold some locks, but then, you know, the garbage collection process might need to take those locks, and then you end up with a deadlock in your application, right? So there is like overhead costs that are associated into going into like common data structure. So each thread have its own thread cache. There is a thread bin also for each size class in the thread cache, and we allocate in batch from the arena, and then we flush what we have in our cache in batch to the arena, and we store the result in the thread cache, meaning that in the fast pass, really, when we allocate, we go see if there is something in the thread cache. If we didn't mess up things, it's going to be true most of the time. We just read one pointer from them, return it to the application, done, the allocation is finished, right? So we are talking like 3-digit number of cycles to do an allocation on the fast pass. And when freeing, you know, similar process, we put them back in the cache. When the cache is full, we push that to the arena. So roughly, this is what the straight cache look like. Notice the beautiful color again. We have an extent map cache. I don't know if I want to dig too much into this, right? It's going to be too long, but essentially it's a way to speed up the reverse lookup from the pointer. And then we have like a series of thread bin for each size class that points it to a buffer that is also in the thread cache for locality, and so that we don't have to allocate a new buffer. We don't want to allocate in the GC because we have a recurrence problem here if we do that. And in that buffer, we store pointers that we allocate in batch from the arena and that we retrieve. And then we have what we call thread bin state. It's like more state associated with each bin that we don't use that often. And so we want to put them at the bottom so that as much as possible fits on one page, so that when you allocate on the fast pass, you're just going to touch one page of memory, at least for smaller bins, which is the one that are the most used. All right, periodically, we're going to, what we say, recycle the bin. Once in a while, we're going to look at the bin and run a small maintenance algorithm on them, if you wish. So what happened is that if the bin has been emptied, maybe I should show that first, right? So that corresponds to the thread bin and the thread bin buffer. We have the buffer in which we store pointers that are allocation of a certain size that we are ready to give over to the application. And when the application frees something, the pointer returns into that buffer as long as there is space. And we keep a series of pointers from that. Obviously, top and bottom is just like the range in the buffer that we can use for that size class. There is no magic business there. The current one is like where we are. So if we were to free a pointer, it would go there below. And if we were to allocate a new one, it would take the bottom one and move the current one up. The low water mark is the lowest value the current has taken since the last recycling operation. That allows us to track a few things that we use for maintenance. So I'm going to go back to this. So when we recycle a bin, if the low water mark reaches 0, and we also refill the bin since the last recycling process, we know that we are not filling that bin enough. Like there is very high demand for that size class in the application. And so we're going to increase the amount of element we batch from the arena every single time we do that, right? So we avoid like running out of element in the cache and needing more. On the other hand, if the low water mark did not reach 0, we know that we allocated too much element in the bin, because since the last recycling, we don't even use all that we have in there. And that means that we're keeping way too many things around and using memory for no good reason. So in that case, we're gonna flush part of the thread cache, and not that next time we need to refill, we're gonna refill a smaller amount. And this way, over time, the thread cache is gonna adapt its behavior to the actual demand of your application in terms of different size classes. To try to not retain too much memory that it's not going to use, but try to also improve performance for the size class that you heavily use. This, works very well in practice. We didn't make it up. Like this whole mechanism exists in GMalloc. We modified it a bit because most of the existing literature about that is about malloc and free, where you have a well-balanced amount of allocation and freeing. But we also want to support the case where people just allocate and never free. So we had to tweak the algorithm a bit, but not that much. And it works well in practice. On the fast pass, when we allocate, we only touch one page on the happy pass. We go in the thread cache, we look at the proper bin that we need. If there is some element in there, we return it, we adjust the current one up, done, end of story. Just touch one page of memory, just return a couple of thread cycle. When we free, we're gonna touch one page in the extent map to load the page descriptor, and then touch the thread cache to put the pointer back in there, and done as well, right? So it ended up being very, very sporadic in resources use. It doesn't clutter your TLB entry for GC-related stuff, which means you have more TLB entry for your application. And if the cache is full or empty or whatever, for some reason it cannot fulfill your request, then you go into some smaller paths that does more expensive stuff. But if we do that well enough, and this is what we see in benchmark, this basically, never happens in a statistical manner. All right. I'm going to hand it over to Steven for appending and finalizing.
Okay. In addition to allocating, we have features in D where we have appendable blocks, meaning that you allocate an array of data and you append to it. It just extends what's actually valid in the block and doesn't have to reallocate that value elsewhere. A lot of you have seen my array article about that. We also have objects that we allocate that need finalization, or the destructors to be called. So we need to store metadata for both of those things. We need to store a finalizer, which is essentially a pointer, and a used size. The way that the DRuntime GC works is it always stores those things in the allocated space. So it has a bit somewhere that says, yes, there's a finalizer, and another bit that says that it's appendable. And if those bits are set, then it has the data stored in the block, and we'll read that when it's needed. This GC stores the data differently based on the size of the allocation. Large allocations are pretty easy. We have this extent record, which is 128 bytes. If you have a large extent, you don't need most of that because most of that's used for bits saying whether the slot is allocated or has metadata and stuff like that. We just have one big segment. Everything can be stored in there. We can put the finalizer, which is just a pointer, and the use size directly in the extent. You can extend a large extent without having to touch allocated memory. The extent record itself just says, okay, you need more data, we're going to extend the extent, and we don't have to write some value inside that block. Slabs, however, don't have enough space in the extent because you have all those bits that are needed. We need 8 bytes to store the finalizer pointer. We store this inside the allocation at the end. DRuntime does basically the same thing, except I think in certain cases it will store it at the front when it has a large block. But in this case, we always store it at the end. As we said before, 8-byte allocations can't support appending or finalization because you would have to take up the entire allocation just for the pointer. If you allocate, let's say, an array of 4 bytes and you want to append to it, it's going to reallocate even though it could extend in that block. That's just the way it's going to be. Unused space instead of used space. In DRuntime, I think I actually wrote this code like in 2008 or something to do the appending and put that stuff in the block, and I store how much data is used. And Amaury came up with a clever way to do this. Instead of storing the used space, he stored the unused space. And the benefit of this is the more space you use in the block, the less space you need to store the unused space. So as you get to the end, like I have 1 byte left, well, you only need 1 byte to say I have 1 byte left. And in fact, you can use up the whole block by just removing that, and now it's no longer appendable. That's pretty clever. Turns out we can actually store both the finalizer and the appendable unused space in the same spot. Remember, this is only for slabs. Large allocations, everything gets put in the extent record. But the largest slab is 14,000 bytes, and that only requires 14 bits for the unused space. We like to use all the bits we can. We have 16 free bits in the finalizer pointer because it only uses 48 bits of address space. So we can stuff the 16 bits at the upper bits of that pointer. We have 14 bits. We have another bit to say whether the finalizer is valid or not. And we have a second bit to say whether we're using 1 byte for the length or 2 bytes for the length. When the finalizer is present, we're always going to use those last 8 bytes regardless. So you can't append into the finalizer or else it would overwrite it. That's going to be the maximum size of the allocation. But if it's not present, then we can go all the way up to the last byte, because as you get larger, that used space gets smaller, and finally you can get rid of it completely. So what this looks like, in memory, we have the finalizer pointer. The 48 significant bits are little endians. They come first. Then at the end, you have the 2 size bytes in big endian form, because we don't know if that first byte is actually used by the allocation, because if you only have 1 byte of free space left that designates free space left, then that could actually be data from the block. So we have a bit to say whether that's valid and a bit to say whether this is valid. And when you load it into the register, it kind of looks like this. So there's some really funky code in the garbage collector to do like a byte swap and figure out what things do we have present. It's actually really clever. When we finalize an allocation, first thing we do is we look up the metadata. If the metadata is present and the finalizer is not null, then we pass the finalizer and use size info to a handler function. The SDC code just calls the function as a pointer. You pass in a pointer saying, okay, I allocate this, and here's the function pointer of the thing that will deallocate it. And it will store that and then call it when you're done. But DRuntime hook must do something different because we do everything based on type info. We're going to get to more of the DRuntime integration in a later section. Amaury's going to handle this part.
Yeah, so before we go into more deeply into the DRuntime integration, we are going to talk quickly about how we do garbage collection, because have you noticed we've been talking to you for like an hour and a half about garbage collector, and we have not said anything about garbage collection, which is I mean, quite a feat. So here we go. The GC right now uses a stop the word, parallel mark, and sweep garbage collection. All those words are important. They mean something. First, during the garbage collection process, we stop all the threads of the application, except the one that triggered the garbage collection, but it's also not doing anything related to your application. It's, orchestrating the garbage collection. So effectively, your program is stopped. Mark and sweep, it's a two-phase garbage collection process where first we explore the heap from a set of roots. So the roots are going to be like the stack of your threads, the global data, and this kind of stuff. And then we track pointer and we mark every single allocation that we find that way. And then we sweep the heap, meaning we go over the whole heap. We look at every single allocation, and the one that doesn't have the mark bit, they are dead, we free them. And the word parallel is also important, meaning that this mark phase especially, which is the second thing that is quite important in terms of resources, like allocating small stuff and mark phase is like literally dominating the profile. Making it parallel helps quite a bit with performance. We're gonna start one thread per CPU core that you have, and all those threads are gonna start marking the heap in parallel. Let's go into more details over those various steps. The one that was the most tricky to get to work was stopping the word. To do that, first, we had to hijack the pthread create function. So if you link the GC in and you call pthread create, it doesn't call the pthread create from pthread, at least not initially. It calls a function that we defined, and that will do some magic and then forward that to the real pthread create function. Then we use signals, like unique signals, and we use the SIGPOR and XCPU signals because those were old signals that were used in the mainframe time and that have not been used for literally decades for their intended purposes, but they've been used by Boehm to do exactly what we're doing. So we pretty much consider that the de facto standard to do that. Boehm is like quite widely used in the C and C++ world. There is no standard saying you need to do that, but it's a bit the de facto standard in the space. Obviously, we do not want to suspend a thread in the middle of a complex operation, in the middle of a GC operation, for instance. When it's playing with the thread cache, it's no problem, but when it's starting to go into the arena, the page filler, the regional allocator, all of that, we don't want to stop in the middle of this, right? Because we're going to mess with the state of the GC itself from under the feet of the thread, and bad things are going to happen. But also, during thread creation, we don't want to do that because all kind of race condition can happen. Users may also need to tell the GC, do not stop my thread during that portion of time, because this is very important to me that this is not interrupted. So we have a mechanism for that, and a lot of complexity come from that because there used to be a mechanism in DRuntime to do that, but when we tried to use it, we figured out that it did not work, and nobody was using it apparently, right? So nobody noticed that it didn't work. So we got rid of it in DRuntime, and we had to implement our own stuff. In the happy path, when you can suspend the thread, it receives the signal, go into the signal handler. The signal handler sees that, okay, we are in the state with that thread where we can suspend. So it's going to just suspend with SIG suspend. We don't even need to dump the state of the CPU on the stack or whatever, do this kind of magic, because we use, like for people that are familiar with the signal IP, the SI SIGinfo flag, which are going to cause the system to push the state of the machine on stack before calling your signal handler and pass a pointer to you, like pointer to a U context. Anyway, all of that ensure that the state that we need to scan is already on the stack, so we can just suspend. It's fine. But if the thread is busy, meaning like this is what we call the state where you cannot suspend the thread. It's busy doing something important. Well, when you enter the busy state, you set a flag somewhere in the thread local information, hey, this thread is busy, right? And it's actually a counter, so you can make it busy several times and exit several times. When the signal is received and the thread is in a busy state, obviously it won't suspend, but it would set another flag that will say, hey, we requested suspension here, but it's not possible to do right now because the thread is in a busy state. So we're just gonna remember that and resume execution of the thread right away so that we don't stop whatever this thread is doing that is so important. And then the thread continues to do its thing. And when it exits the busy state, it checks, hey, is this flag that we are supposed to suspend, has it been raised? And if not, then just resume execution, exit busy state does nothing, fine. But if the state is set, then we push all the state of the CPU on stack, and we call suspend, like SIG suspend, to suspend the state of the thread. So we're gonna wait basically until we exit the busy state to suspend the thread. How do we hijack pthread create? That's an interesting one. It's a bit of an explanation here, but it's simplified because, with sanitizer and stuff like that, we had to make that work with that as well. Basically, the idea is like you define pthread create in your library. And because your library is linked in before the system one, then it's got to call your pthread create. But now the problem that you have is like, how do you call the real one? To do that, we call what's called a trampoline. So a trampoline is going to be a global function pointer that initially point to a function of ours. And that function use DLSym, which is a library provided by the dynamic linker, to find the real symbol. Once the trampoline finds the real symbol, it's going to replace itself by the real thing. So the first time you call the trampoline, it's going to do some symbol resolution and then replace itself by the real guy. And any subsequent call to the trampoline is directly going to call the real pthread function. We don't need to do anything special for initialization. It's fairly cheap except the first call, and it intercepts like any thread creation unless you do like syscall to the kernel directly. But then if you do that, you're on your own. Mark phase. This is the bulk of the work that the garbage collection process needs to do. Like everything else is very cheap in comparison to that. So it was quite important to make it parallel. Otherwise, we can do everything much better than the current GC. If that is not parallel, it doesn't matter, right? we're just much worse. We're gonna create one thread per core in the machine, and those we call worker thread. And then we're gonna start to put the root into some work list. And all the threads are in the loop. Is there some work for me in the work list? If there is, I'm picking it. I started to scan. And when I'm done with that, I'm gonna wait on the work list again. And so we put stuff on the work list. It's like very simple. It's a stack with a lock, essentially. When none of the threads have anything to do anymore, then all the worker thread exit, right? Because it's not because there is nothing in the stack that, there is not something that is going to come later, right? So as long as one thread is still scanning stuff, there might be more stuff coming in the work list. When all the threads are waiting on the work list, effectively, this is done and they exit. What does the worker thread do? Well, the worker has its own work list, right? So there is the worker work list and there is the shared work list, right? And if the worker have nothing on its work list, then it's going to go to the shared one and pick one element on there. Each element is going to be a range to scan for pointer. So it's going to do that and check that is this in range, that it could be a hit pointer, because this is very cheap. This is one subtraction, one compare, and we can evict the vast majority of false pointer that way. Then we're going to do lookup in the extent map to find like what is in there. Is it a slab, a large allocation, or nothing? And then depending on that, if there is something, we're going to mark it. And then we're doing something maybe a bit clever, but we find to get like a lot of performance out of that strategy. If we find some further pointer to scan in there, what do we do? Well, if our own work list is empty, we just add it to the work list and keep going, right? But if we have item on that work list, and what we scan is a large allocation, we are going to put it to the shared work list. And if it's a small one, we are going to add it to the worker's work list.
What does it mean to find a pointer? How to distinguish between a couple of bytes and a pointer?
Yeah, so effectively we're reading the memory, and something are going to be pointers in there and something are going to be like random data. So we have a two-step process to recognize what is a pointer. First, we're going to check, we have like, what is the higher possible pointer address in the heap and what is the lower possible address in the heap. And if it's between the two, we consider that it may be a pointer, but if it's outside of that, we eject. And then we do a lookup in the extent map, that thing. So we do like a two-level lookup in there. If we find a 0, then there is nothing there. But if we find something, it's going to be a slab or large allocation or something like that, and we are going to consider that this is a pointer to that thing. And that could be a false positive, but what we find by measuring is that it happens a lot on 32-bit system, but on 64-bit system, you don't get that many false positives. Because the address space is just like big enough so that it just doesn't happen as often. So for small allocation, we put it back on the worker's work list. That allows us to blast through graph of small objects, right? If we don't do that for small objects, we were gonna run into a performance problem. But for large one, we give the opportunity to another thread to pick it up and scan it. And obviously, because we have our own work list in the worker, if it gets too big, we flush it to the shared one. And that's how it works. We get like very good fan out of that. It's much better than the current GC. So if there is like, some fan out in your graph of object, we're gonna like destroy the existing implementation. If there is no fan out, then it's gonna be pretty much the same because you are following a linked list effectively. And there is not much we can do, right? It's gonna be loading memory that is the limiting factor. All right, and then we do a sweep phase, very simple. We go over all the arena that are initialized. In those, we go over all the page filler. We go over all the blocks, all the allocation in each blocks. If it's marked, we keep it. If it's not marked, we throw it away. And then we go over the block and we purge the page of the block that are unused if there are too many of them. Very simple. There's a bit more details in there, but essentially like sweep phase, very simple. All right, so we're gonna go back to the runtime integration with Steven where he left off.
Okay, so for those who don't know, SDC is a compiler that we use to build our GC. Hooking the SDC GC from DRuntime is somewhat complicated for a few reasons. SDC GC does not have access to DRuntime. I don't even think SDC supports classes or anything, right?
It supports classes. Yeah.
It does? Okay.
Yeah.
Well, there's a lot of things that SDC does not support. There's no way it would be able to use the type info properly. So we have our own scheme for array metadata and finalizers. When we first wanted to look at integrating this stuff, I looked at the interface for the GC, and the interface for the GC has a lot of implementation details from the existing DRuntime GC. So we're doing some stuff differently. You saw how the metadata works. The way it works in DRuntime is mostly different. We have our own way of doing it, and DRuntime has an expectation in the array runtime that the GC is doing certain things, and it's going to use those things to implement array appendability and finalizers, which we are taking over in the GC. So what we need to do is move that functionality from DRuntime into the DRuntime GC itself. So it's an abstract piece of functionality. This qalloc function, which is something I think I added, actually. I think you were saying, Attila, like you look back, who did this? Oh, it was me. That was added when we did the array runtime back when I created it. And that function basically returns a structure that tells you information about that block that is very specific to the current GC. So we kind of have to deal with that, because if we're going to implement that, we have to replace that thing. There are also odd API functions that were required. I found out there was a function called collect no stack. When I looked at what it did, it does exactly what it says. It runs a garbage collection without scanning the stack, which seems like a really horrible idea. But it was only ever called from the end, from GC destroyer, or the thing that says, okay, the GC is going away. And the reason I think that was done is because people would make an application, allocate something, and then people were trying out the language. Hey, how come this didn't clean up my block? The GC is not working. It's not cleaning up this block. And it's because some leftover piece of stack data was pointing at it. So I'm assuming that at some point somebody said, well, we'll just not scan the stack at the end of the application, and then those problems will go away. So I decided we shouldn't have this function, because to have a public API where you could just totally destroy all your memory and corrupt it is a bad idea. So we've actually got that removed. And of course, the SDC API is different from DMDs. So for instance, the arguments are passed in reversed order, which is the way that C does it, but apparently DMD has a different API for that. In order to accommodate our new way of doing array allocation, I created this interface, this array metadata. The GC is going to be responsible for this stuff. So it passes you back this generic struct. When you call these functions, it's actually going to call into the GC and say, okay, do your thing to do the array metadata. And that's all handled now by the DRuntime GC, and then also by the SDC GC in its own way. So now all that functionality that was built into the array runtime is now all in the GC. It should provide a way to eliminate a lot of code. I think eventually we're going to get rid of the file in RT lifetime that does all this. It's not there. It's not done yet, but we'll get there. So removing implementation details from the interface. The GC interface accepts type info for a lot of things for malloc, but really the only things it uses are the precise scanning bitmap that's stored by RT info, which is a template that runs on every type info and stores basically the bitmap pointer from the compiler, which is kind of crazy. that we do that for every type info. But now that we have templates to do all the allocations, we have that information without needing type info. So we can just pass that bitmap directly in. It's only needed for the precise scanner in DRuntime, but it's still needed for the API. We don't use it because we're completely conservative. The other thing is calling the finalizer from type info. So this piece we still have to do, but at some point I think we might actually still use a template to generate a specialized function that does the deallocation. That might be more effective than using type info. Because I think you said yesterday that that one of the bigger things that we're dealing with is just in the glue to call SDC GC is looking up things in type info because it's just so painful.
So quickly, as we've seen for allocation and freeing of small allocation, which is the vast majority of allocation in practice, we touch one page on allocation, two on the allocation, except we also touch the type info. We touch the static data where the pointer to the GC object is, and then we touch the GC object, and then we touch the virtual
just many
the virtual function table of the GC object, and then we call into our stuff. So we end up like touching memory all over the place to then call that function that is super optimized. As a result, this code that doesn't do very much except fetching various data end up taking half the time.
So eventually we're probably going to get rid of that. Deprecate the qalloc function. I don't think we need it anymore, especially if the GC is handling mostly used for the array runtime. The struct final bit no longer has to be part of the API. The SDC GC is doing it differently, but it's still internally used by DRuntime to mark, hey, this block has a finalizer in it. Miscellaneous hook problems, like I said, the ABI is different, so we have to use external C functions for all our hooks. This took a while to figure out, but there's actually a function in GC proxy, if you look it up, that basically says load a function pointer to all the GC registration functions and compare them, and doesn't do anything after that, just so that it could keep a reference to the GC in there. Otherwise, it'll say, hey, I don't know where this function doesn't exist because you're never calling it. We had to do some extra hooks for stopping the world because we needed those features. And obviously, class finalization doesn't fit with the SDC scheme because the finalizer pointer is not stored in the block, it's stored in the class. So I store a finalizer of 1, and that just is a signal that, hey, the finalizer is in the block. So that works out pretty well. Future possibilities.
We've structured everything so that we can use a strategy that's been pioneered by Boehm, which is essentially like put a write barrier over anything in memory that may contain pointer, do the mark phase concurrently with the program still executing, then stop the word and redo a mark phase starting from the pieces that were touched by the program during the time you did the first one. If you do that, everything is already marked pretty much, except for a couple of race conditions. So the second one is very, very quick. As a result, you can get like a mostly stop the word situation there. You can never like statically bound how much you stop the word because if the second phase takes too long, you can like degrade it into phase 1 and redo a second phase 2 later. So you can like put hard limit on how much you stop the word. We have designed all the data structure and everything so that we can do that easily. We can do it better than Boehm actually because we split the allocation that contains pointer and the one that do not, what Boehm cannot do. So we have very good hope that this is going to yield interesting result, but it's not going to be in the V1.
And this part is a little controversial, I think, but we are looking at possibly replacing the C allocator with our allocator. This means you can use C libraries, and they'll also use the GC to allocate. Theoretically, you would no longer have to worry about pinning memory that you pass to a C function because the functions are all scanned because we're hooking pthread create, and the data structures that it might use are all allocated by the GC. So it would be scanned as well. It's still experimental, and if we do turn this on, it's like false immediately, so we have to leave it turned off for now, but it does work when you just run SDC.
It does work with SDC when you don't have DRuntime, but DRuntime is doing something weird that crashes when we do that.
And a couple of miscellaneous items. This is not exactly ready yet, but there's a couple PRs we got to make for DMD to enable an actual dub package. So you should be able to download a dub package and run this GC as a test. More platforms, Windows and OS X, tweaking heuristics and telemetry for tuning would be nice to have, I think as somebody mentioned yesterday. And that's it.
The original GC I wrote is, very old, and its major feature is it worked. I'm not kidding. Its major feature, it worked, and it was, bug free. But obviously, a modern GC is needed, and after listening to your presentations. You two are the most qualified people to do this kind of work. And I thank you, and I really appreciate it.
Thank you.
So, a lot of those techniques we didn't came up. We actually like dug into geomalloc and tcmalloc and Boehm and memalloc and like everything, you know, that existed in the space. And some of the thing they do is documented, but most of the thing they do is just in the code, right? So we've been on the reading like a lot of various allocators. So some of the tricks are from us, but like 90% of it, we actually like look at what the big boys are doing and
pthread create and everything that you're hijacking and the signals, how does that translate to Windows in any way, shape, or form?
The technique that we use to hijack pthread create, we can use also to hijack the thread creation on Windows. The signal one, like, it's one of those things, there is a very nice API on Windows to suspend threads. So it's actually quite easy to suspend thread on Windows. On Linux or other Unix system, you have to use Signal or some like other mechanism. It's full of race condition. There are like a lot of snakes in there. It's horrible. But, you know, such is life. Sometimes Windows is better.
Just to mention also that the current DRuntime uses thread signals to do thread suspension on Linux and also has a mechanism for Windows. So, and Boehm also does very similar things.
The things you were talking about, like deprecating QLock and blah, 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 has that been merged already?
No, that's what I'm saying. I need to make these.
Right.
So I've made a complete branch of or a fork of DMD just to test these things out to get it to the point. And now that I know what needs to happen, I need to go make PRs for the actual DRuntime.
We've merged a couple of them related to stop the word functionality to like, you know, not stop certain thread. We needed some modification in the runtime, but yeah, for the array support, we have not started merging.
I was making a list of questions while you were speaking, so I've got a bunch. So if you'll indulge me.
Let me sit down.
My first question is, what about 32-bit systems?
We don't plan to support those.
Yeah,
So you're gonna have to use the old GC if you want to use those. Yeah.
What would actually be really cool and interesting to me is to run the GC as kind of a leak detector. Like if I write software that does explicit memory management, having the GC there to find leaks is pretty cool. How are your data structures compatible with storing metadata and allocations, for instance, like line file references or, you know, alloc frequency references and things that might come from like debug info injection?
Yeah, so right now we don't do that. I don't know what would it take to do for small allocation. We probably would have to reserve another pointer for small allocation to store this kind of information. For large allocation, it wouldn't be a problem at all to do. We have plenty of bits here and there to reuse to do that. That's an interesting idea, though. I would be careful about using that because you're going to have some false positives in there, right? It's not going to be a perfect oracle, but I know people use Boehm in that way and find value of it. So that's yeah.
Yeah, it's a handy tool. It's probably worth thinking about just making sure that's possible. You mentioned having thread pools and things like that. I don't think I've ever worked on a project where I don't have a set of like a thread pool with a bunch of workers that are as many as there are threads on the system. Would you conceive of an API to allow your work to run on my 3 existing thread pool rather than having a whole nother separate thread pool?
No, and there are reasons for that. The reason is like the C runtime is doing funky stuff when starting and stopping the thread with memory that might be allocated on the GC actually if we use malloc and free. So we need to like start and stop those threads in a very, very specific manner or everything explodes spectacularly. Yeah, that doesn't sound realistic to hook that into a third-party thread pool.
You were describing, doing array concatenation and expanding arrays and stuff. Is the allocation layout optimized to improve the probability of a successful expansion? Are you filling memory in a sort of a linear fashion, or are you filling it in a scattered fashion so that an array expansion might not need to move when it reallocs?
There is a feature in the existing GC and the new GC to take a large allocation and say, I want to just keep extending into further pages.
Yep.
And we are going to allow that for large allocations. For slabs, you can't concatenate 2 slabs together, slab slots. So you'll have to reallocate at that point.
Cheers. Thanks, guys.
Do you recognize thread local storage, or is it one big heap, or how does it work when you have a thread? Can you because
No, I get it. It's one big heap, and the reason is if we want to eject malloc free and get the application going, we're not gonna have the information as to whether the memory that is allocated is shared or thread local, right? So you end up not being able to separate thread local heaps. Though in practice, because the worker recurs on small allocation on its own work list, it tends to, even though there is no explicit specification, it tends to create a situation where each worker, scan its own subgraph or object that's going to correspond to your application thread.
If you think about you create a data structure with a bunch of nodes, you're just going to allocate a bunch of these things in the same page, right? So this one points to that one. I look at that, it's in the same page. It's going to take no time at all to scan through all those things.
Mm-hmm.
If you have a statically linked executable Golang style, how does the DLSym work for pthread create?
In the case of pthread, it's always a shared library. And there is even a .a. Like if you look on most Linux distro, there is a .a that is appeared to be a static object that you can statically link. But actually, that's a linker script that dynamically linked the one from the system. They are quite smart. And the reason is the implementation in pthread is like heavily system dependent, right? So if you were to statically link a pthread version, you share the executable to another person with, another computer, it's not going to work properly.
Cool. Thank you.
All right, I think we're going to cut off the questions there because it's about midday. So I'm sure you guys can harass these guys downstairs if you have anything else to ask. But until then, round of applause.